All right, so yesterday we finished off here, but I want to go back and add a few things to this slide. And the first thing that I want you guys to add, ow, that hurt. When it says separation of mixtures, I want you to write the word physically. Okay. We're physically going to separate things. Okay. Now, some of these techniques are more challenging than others. But I think it's important that we talk about how we can do those. So the separation techniques exploit different component properties. I know that's kind of worded weird. Sorting by color, sorting by magnetism. Let's talk about a few other ways that we can sort. So what are some other things that we can sort by? Size. We've already got color. So we've got color, we've got magnetism, we've got size. We can do weight. There's a big one that I'm looking for. Say it again. Density. How can we separate things by density? Okay. Can you separate blood by density? How? Spin it really fast. Okay. So these are just different ways that we can separate things based on their based on their physical properties. So come right here beside filtration. Does anyone remember what we would be separating it by in terms of filtration? There's two things. What'd you say? Solid and liquid. What's one word to combine both of those? State of matter. Okay. We're going to separate things by their state of matter. So we're going to separate things by solids from liquids. Okay. Distillation. Does anyone remember what we're using distillation to separate by? Very good. Boiling point. Now, again, this is something that I keep harping on. Is the boiling point, the melting point, the freezing point, the vaporization point, are all those physical changes or chemical changes? Physical. Okay? So, nothing changes. It's still what it is. Even though you are boiling fingernail polish, do you still have water and do you still have acetone? Why did we boil it? To separate it. Very good. So that's the whole reason. And then chromatography. What do we use chromatography for? What did it use to separate? Color. Very good. Now, there's another word that I want you to actually add because, yes, color is what you visibly see, but what causes the colors to separate, Teddy? The polarity. Very good. Okay? Because what we discussed yesterday was the fact that every different color is a different molecule, and the different molecules have different polarities. And that's what chromatography leads to, is determining which color or which molecule is the most polar. So again, looking at that right picture over there, which color would be the most polar and how do you know? Very good. So if you didn't write this yesterday, I know that's really hard to see, so let's clear that. Let's change it to purple. So up here, actually let's change it to blue to make it match. Okay. Most polar, and then what would be the bottom? Least polar. Very good. Least polar. Now, I'm going to throw a curveball at you. Yesterday, what did we say this little filter paper was dipped in? Alcohol. Is alcohol polar or non-polar? It's polar. If y'all didn't write that down, I'd write that underneath it. That the alcohol is a polar solvent. Okay. We also talked about how like dissolves like, but I don't like that. Okay. I don't approve of that phrase. Because if polar dissolves polar, we also said that non-polar dissolves non-polar. If I change this solution and I change it to a non-polar solution, what will happen to the black Sharpie dot? Nothing. Why will nothing happen? Because the colored molecules are what? Polar, and the solution is non-polar. Will they interact? No, they will not. Okay. There's something you can do with leaves when you grind leaves up and you mix it with a certain chemical, this non-polar, you can actually make a dot of leaf dyes, and you can actually separate the color of leaves the exact same way, but those molecules are non-polar, whereas a Sharpie color is polar. So it's kind of interesting. You can actually do it both ways. Okay? All right, so let's completely shift gears. So now we've talked about mixtures. Okay, there was two other words for mixtures. What was when you think of a liquid mixture, what do we call that? Solution. When we think about a metal mixture, what do we call that? An alloy. Very good. So that's out of the picture. Now we're getting into pure substances. Okay, so this is the chemical properties of what we're really going to focus on. These are chemical properties. So pure substances have fixed composition. What does it mean to be fixed? It's set. You can't change it, right? It's done. Water is always what? H2O. Carbon dioxide is always CO2. Sodium chloride is always NaCl. Okay, it's always those things. You can't change it. If you change it, you're breaking the chemical properties. A pure substance is either compounds or elements. Which one of those two can you break into smaller pieces? Compounds. And what do you break compounds into? Elements. Very good. A pure substance differs from the mixture in the following ways. Every sample of a given pure substance has exactly the same characteristics and properties. Which means if you have a handful of sugar or a room full of sugar, does all of it have the same characteristical properties? Yes. Okay. Every sample given pure substance, every sample of a given pure substance has exactly the same composition. That's exactly what I said. Water's always H2O. Carbon dioxide is always CO2. If you change any part of that, have you changed what it is? Yes. And the last part is the hardest thing to understand. Is the same percent by mass. We're going to get into percent by mass later on, but I want to give you just kind of a snapshot of it real quick. Water is always 11.2% hydrogen and 88.8% oxygen by mass, no matter how much you have of it. Okay? No matter how much you have of it. So I could have a handful or a roomful, and it's 11% hydrogen, 88% oxygen, no matter what. Why is that true? Because for every water, how many hydrogen do you have? 2, and every oxygen you only have 1. But here's the scary part. Not scary, but here's the weird part. If you have 2 hydrogens for every 1 oxygen, why is the percent significantly lower? What are we comparing? The percent by what? The percent by mass, right? Percent by mass. So if the oxygen, even though there's only 1 of them, is significantly greater percentage, what does that tell you about the mass of oxygen? It's significantly higher. Well, let's look at it. Do me a favor. If you've got some room around the slide, I want you to write this. And I cannot stress to you how important this little phrase is going to be for us over the next year. Okay, I cannot stress to you how important that little phrase is. The basic definition of a percent is what? Part over whole. Part over whole. Part over whole. So when we're talking about water, what's the whole thing? H2O. How many parts are there? 2 parts. So let's think about this. So if I want to know the percent of hydrogen in water. Now, we're talking about percent mass, right? So if you want to write that in as well. The percent of the mass of hydrogen in water. I need to know the part over the whole. Let's start with the easy part. If you look up here on the periodic table and you look up for the mass of hydrogen, okay, can anyone see the mass? I know it's a really long ways away. Okay, it's 1 point something, something, something. Let me go ahead and tell you this. This is for future knowledge. Anytime we use that thing hanging on the wall for masses, you always round to 2 decimal places. Okay, and I can assure you, a lot of these you'll memorize. Madison, is that true? Will you memorize most of these? Thank you. Okay. I'm telling you, you will use them so much you'll quit looking at that thing because you'll have them memorized. Hydrogen's one of them that you'll memorize. Okay. Now, do you agree that is the part? But here's the problem. For every one water, how many hydrogens do you have? 2. So technically, this is not right. It's 2.02. So you can do one of two things. You can either erase that, and you can write 2.02, or you can do times 2 for the 2 hydrogens. Either one, I don't care what you do. Me personally, I'd write 2.02, but I'm trying to explain it at this point. Now, what is the whole thing? What does that mean? That's the mass of the entire water molecule. There's only one mass of one compound I need you to memorize, and you're fixing to see it for the first time. And it's the mass of water. That is the mass of a water molecule. That's the only mass of a compound I'm asking you guys to memorize. The only one. And I'm going to teach you how to do it later, but it's not that hard. So let me ask you something. So we know that the part is 2.02, right? We know the whole thing is 18.02. You all have calculators on your phone. Somebody divide that number for me. 2.02 divided by 18.02. Tell me what you get. Oh, by the way, did you do this? I apologize. I forgot to say that as well. Make sure you multiply it times 100. Does that number look familiar? That's where it came from. Okay? Now, that's the percent of hydrogen. If I wanted to find the percent of oxygen, if I wanted to do it the exact same way, what's the only, other than the answer, obviously, but what part of my math would have to change? The part, okay? Because oxygen has a different part. So we're going to do percent mass of oxygen. Now, the only mass that I asked you to memorize is water. What is it again? 18.02. Now I need the part of what oxygen weighs. When you look up there, it's it's 15.9999 something. Okay? How many decimal places? 2. So 15.999 rounds up to be what? 16. Okay? And back we can come in and we can do this as well. Again, I assure you these numbers will become ingrained into your skull over the next several weeks. Somebody do that math for me. Multiply it times 100 at the end. Amazing. That number looks very similar as well, right? So that's how you determine percent by mass. Any questions? And again, we'll get into this later on as well. All right, so the last part of this is the elements. And a lot of this stuff you know. So this is the part where I think it's interesting to kind of stop and pause. Because at the very beginning of the year, whenever you guys first started learning the element symbols, some of them were really weird and some of them were understandable. The ones that were weird, like tungsten, like mercury, like iron, like lead. How do you get Pb from lead? How do you get Fe from iron? How do you get W from tungsten? Okay? So it comes from their Latin or Greek roots, even Roman in some cases. And so what happened is because most of these right here are old elements, and what I mean by old or ancient is they've been around for millenniums. And so they already had a name. And so when we transferred the name from whatever the root was or the origin to English, it didn't get changed as far as the symbol. The symbol stayed the same. So this is why some of these names, the English version, do not match their symbol. And so like antimony. Antimony's SB, and you're like, where in the world did that come from? Well, because its ancient root was stibium. Okay? Copper was cuprum. Gold was aurum. Iron was ferrum. Lead, I like that one. Plumbum. Okay? And then mercury. What does that say? Hydrogerum. Okay? That's always a fun one. So again, potassium is K. It came from calum. Silver's Ag. It came from argentum. Sodium was natrium. Tin was stannum. And tungsten was wolfram. So when you see these names, now it makes sense. I get it. Okay, I can see why tungsten is W if it came from wolfram. All those things kind of make logical sense. And the reason they didn't change the symbol was because most of these were in such use at that point around the world, they could not change it just because the language of origin changed. Okay, so they left them as they were. So again, to us it doesn't make sense, but to the rest of the world that uses the Latin root, it does make sense. I agree. Why didn't we just keep them the name? Keep them the same? I personally think, well, duh, why change it to what makes sense to us? Just leave it alone. I agree with you. But apparently we have to be the complicated country that we are. Okay? I don't know. So, yes, ma'am. That's a question for Miss Weekly and Miss Odegaard. I don't know. That's actually a question I want to know the answer to. Like, take them this list and say, hey, how did they pronounce these in Spanish? Just ask them. Like, I would like to know that as well. Anybody got them? Ask them. I really want to know. I really want to know. Yeah, the symbols are, yes, most definitely the same. Okay? Real quick. Tomorrow, when you get your periodic table, you got to draw in color. I'm telling you now, the colors aren't the same as this, but this may help you as far as being able to label some of it, okay? So it's very similar to this. Do not use these colors. Use the colors that are on your sheet. All right, so let's get through this. I need to get through this. I know we're running out of time, but I have to get through this, okay? Because this stuff is on your test with or without me going over it or not. And you'll learn this all tomorrow. What does vertical mean? Very good. Up and down. So when you're going up and down, those are called groups or families. Does anyone know how many groups are there on the periodic table? There are 18 groups. Okay? There are 18 groups. So as you move left to right, there are 18 columns. The important thing about the groups is they have similar chemical properties. Now, there is some asterisks in there in terms of there are a few exceptions, especially when you get over here on this far right side and you deal with the stair-step line. There are some weird exceptions. Our horizontal, what does that mean? Left to right. Those things are called periods. Okay? Think about this. When you're reading in a book, how do you read? What direction? Left to right. Okay? Here's the cool thing about this. How many periods do you have in a day at school? 7. There are 7 periods on the periodic table. Okay? There are 7 of them. That actually helps out. That's mentally helping. Okay? The thing as you move across the periodic table left to right, things are going to drastically and dramatically change. So periods, just like words change, elements change. In groups, as you go down, there are some very similar properties, and we'll talk about those properties later on. But like I said, once you get over here to the right side, it gets kind of weird. There are some exceptions. Metals, we already know this. Okay, metal is an element that is a good electrical conductor and a good heat conductor. Bottom line, are there some that are better than others? Obviously. Okay, the two things that I need you to put a star beside and make sure you know these two words are malleable and ductile. Malleable's easy to remember. The way I think of malleable is like a mallet. What is a mallet? It's a rubber hammer. If you hit something with it, it'll turn into a flat sheet. That's malleable. Ductile means it can be pulled into a thin wire. So again, if you're highlighting stuff, I would highlight those two things. So malleable is a thin sheet, and ductile is a thin wire. Okay, and obviously they conduct electricity. Most are solids at room temperature. There's one metal that's a liquid at room temperature. Who is it? Mercury. Very good. Okay. Here's an example. You've got gold, copper, and aluminum. Non-metals. Okay, they are not metals. They're poor conductors of heat and electricity. Many are gases. When it says solids are brittle, what does brittle mean? It can break. So it's really a powder, if you will. And we'll see a picture in a second. They're poor conductors of heat and electricity. So these are pictures of carbon, sulfur, phosphorus, iodine. As weird as it sounds, are they still solid? Yeah, they're just really fine, grainy powder. You would say salt is a solid, right? It's just really small pieces. Again, it's going to stay in the powdery form. And then finally, the metalloids. This is the weirdest group. Do me a favor, beside the word metalloid, write stair, step, line. Okay? On all three of the periodic tables, that one over there on the right side by the door is bright orange. The one closest to me is the hardest to see. It's that blue color, and then the one further back is red. That is the stair-step line. The metalloids hug that line. They're attached to it. They're touching it. There's one major element that's touching that line that is not a metalloid. Who is it? Aluminum. If you look at it, it's number 13. Okay? That is one element that's touching that line that's not a metalloid. Should you already know that? You know aluminum is a metal. Most of the rest of them, there's one exception down there at the bottom. We'll talk about it. But it is not a metalloid as well. But aluminum is the big one. Don't say aluminum is a metalloid. Say that again. Everyone but aluminum. Okay. And then the noble gases, group 18. I can't stress to you how important this group is going to be to us. They are the very far right group. They're the one in the tall column on the right with helium. They are generally unreactive. And I know we're running out of time, but I want to ask this question. What makes them unreactive? I want you to write this word. They have a full octet. Now, what is oct prefix? 8. How many does your valence shell need? 8. If it's full, does it need to gain or lose any electrons? That's why it's unreactive. Okay? All right, we are done.